Hi there, Rachel Chase here, and in the second part to our correlation analysis series, we're going to look at linear regression. Linear regression goes by a couple of names, for example, linear modeling or just modeling, or even calling something a line of best fit. Essentially, both of these things are saying if you find a linear regression model, you're going to find an equation that best approximates your set of data. Now, formulas we need for this are as follows. The linear regression model is equal to y hat, which is a plus b x hat. X and y hat are both predictors, and then this is a series of nested formulas. So you have your equation for b, which equals to r, the correlation coefficient, times the standard deviation of y over the standard deviation of x, and a is equal to y hat minus bx hat. So they're all based off of one another, because in order to get this equation, you need to know what b is. To get what b is, you need to know what r is, and so on and so forth. So let's take a moment and calculate the linear regression model for what we had found before. Point out here, visually, what are these formulas doing? These formulas are trying to minimize the distance between all of the points on your graph. Using the data we found before in the Haverty's advertising expense model, let's go ahead and calculate what our line of best fit would be. Well, we know that our correlation coefficient was equal to 0.967, so that will allow us to find b. b is equal to 0.967 times the standard deviation of y, 2.94, divided by the standard deviation of x, 1.29. Which gives us 2.203, or just 2.2 to keep it simple for now. And a is equal to y hat 7 minus b 2.2 times x hat of 2.5. So that would be 7 minus 5.5, which gives us 1.5. If we piece this all together, we get that our correlation analysis, in other words, our linear regression model, if you will, is equal to a, 1.5, plus, since b is positive, 2.2 x hat. So that means that this equation will best estimate what's happening with our data. So again, visually, what is this doing? If we go back to what we looked at with our first scatter plot way back here, and you say, okay, well, what's the equation? Our equation was y hat equals 1.5 plus 2.2 x hat. That means our y-intercept is at 1.5, which is right around here. And a slope of 2.2 means go up 2 and a little bit more over 1. Up 1, 2 and a little more over 1. So if you take a look here, you can see that this line roughly estimates what's happening within our data set. So that line has just given us the approximation for what's happening within our data set. So to finish up our discussion on linear regression and how all of this works, what you're doing is you're basically finding something to be able to estimate your data. Now we still have to determine, as we mentioned earlier, is this line actually a good fit? So for this, you need your critical values for correlation coefficient, and this will be provided anytime you need it. At a significance level of 0.05, determine if the regression model found in example 3 is a good linear fit. So if we take a look at our table, when alpha is 0.05 and we have n equals 4, we get a critical, in other words, we call this our crit, and that's equal to whatever number you see on here. So our crit is 0.95. What you do is then compare this to what you had found for R. We found our R to be 0.967. If in fact your value of R is bigger in absolute value, and we can see that 0.967 is in fact bigger than 0.95, we can say that this model is a good linear fit. So that means it's acceptable to use the model that we have found. Next up, let's answer a couple of questions based off of our model. To do this, you have to first understand the difference between interpolation and extrapolation. Interpolation is estimating what's happening with your data within the bounds of your set. So for example, all of our numbers, if we go back over here, all of our data went between 1 and 4. You can see that from our advertising expense. So interpolation would be estimating anywhere between 1 and 4. Extrapolation is going beyond those boundaries. So extrapolate means to exceed the bounds. And it could be on the left, it could be on the right. There's no restriction on that. If we assume that the model is a good fit, which we did find it was, I'm just going to copy our model again. Answer a few questions. How much revenue could the owner expect to see if they spend $3.5 million in advertising? X is the advertising expense, so plug in. Y hat equals 1.5 plus 2.2 times 3.5, since that's our X value. Go to your calculator, 2.2 times 3.5, and then add 1.5 to that. So this means that if we spend $3.5 million in advertising, we can expect approximately $9.2 million in sales revenue. This is an example of interpolation because 3.5 falls between 1 and 4. In the next example, you see that we're asking about spending $6 million in advertising. Well, we spend $6 million, that's beyond the bounds of our set, but we can still plug into our formula. So what do we get here? Do the same thing as before, 2.2 times 6, add your 1.5 to that. We can expect 14.7 million. And you'll see here, the next question says, what could be problematic about extrapolation? Quite frankly, extrapolation is acceptable within pretty close range of whatever your data set is. One problem you run into, however, is if you try to extrapolate too far into the future or too far away from what you already have. For example, if you look at advertising expense and sales revenue, if we go way back up here to our scatter plot, does this trend seem like it could continue indefinitely? So for example, if we spent, I don't know, $10 million, maybe we're somewhere over here in terms of where that estimate would be. Does it seem practical that that could actually give you an accurate prediction? And one thing you have to say is, going too far beyond your bounds, your model may no longer be relevant. And the reason for that is something like sales revenue, you have to consider might have kind of diminishing returns over time. So while it might look linear here, it could eventually just kind of taper off and hit sort of a ceiling, if you will. So that's really the only problem we have to concern ourselves with extrapolation, is going too far away from the data. The last thing to always think about with correlation, so what is the biggest takeaway, is the fact that correlation does not imply causation. And the reason I drill this into all of my students is because just because a correlation exists does not mean that there is a cause-effect relationship. Again, you think about the study time versus GPA example, a correlation will probably exist, but that does not necessarily mean that because you study, you will also do well. It's just kind of a, if it works out well, if things go as expected, it might, but it's not necessarily cause effect. That concludes the introduction that and really just kind of the basics that we go over in terms of correlation analysis. Thanks for watching.